Ever wonder if a machine could actually imagine? Not just copy-paste, not just remixing things it's already seen, but genuinely create something from scratch? Well, today we're diving into a really groundbreaking paper that gave us one of the first big answers to that question. And it all starts with a little test. Okay, so take a look at these two grids of handwritten numbers. One of these sets was written by a real person. The other? Totally dreamed up, pixel by pixel, by an algorithm. So, which is which? Got your guess? Well, here's the twist. They were both made by a computer. So yeah, the real question isn't which one is fake.
The real question is, how on earth is this possible, right? How does a machine learn the idea of a number, the very essence of it, so well that it can just create brand new ones that nobody has ever written before? Well, that's exactly what we're going to unpack today. So here's our game plan. We're going to start with the massive problem that seemed impossible to solve. Then we'll get into the brilliant two-part solution they came up with. We'll even look at a super clever mathematical trick that made the whole thing possible. After that, we get to see the payoff, this amazing map of ideas. And finally, we'll talk about what this all means for the future.
All right, first up, the big intractable problem. See, if you want to teach a machine to generate, let's say, a new cat picture, it can't just memorize all the cat pictures it's ever seen. That's just copying. It has to understand the essence of catness, the underlying rules. And for a really long time, the math required to do that was, well, it was a total brick wall. The key idea we need to wrap our heads around is something called latent variables. It sounds complicated, but just think of it as the secret recipe. So for a handwritten 7, the recipe might have ingredients like how much slant, how sharp is the top corner, and does it have a little line through the middle? Every piece of complex data has one of these hidden recipes, and figuring out that recipe, that was the big challenge. And for a long, long time, the math needed to find that recipe was, and this is the word the authors use, intractable. That's basically a fancy way of saying, forget about it. It was just impossible to compute in any realistic amount of time. You couldn't just solve an equation and get the perfect recipe for a picture. No way. And it wasn't just one thing. The authors were staring down a whole bunch of challenges at once. They needed something that could chew through massive data sets. It had to work even when the core math was literally unsolvable. And on top of all that, it had to be efficient, working with just little chunks of data at a time. The old methods, they just couldn't tick all those boxes. So what do you do when you're faced with an impossible math problem? Well, you don't solve it, you find a clever way around it. You change the game. And that's exactly what the authors, Diederik Kingma and Max Welling, did. They created this elegant system with two parts, a kind of neural network duo. I like to think of them as a critic and an artist working in tandem. Here's how this team works. First, you've got the encoder. Think of this one as the art critic. It looks at a real image, like a handwritten 4, and it breaks it down, figuring out that secret recipe we talked about. Then you have the decoder, and that's our artist. It takes the recipe from the critic and tries to draw a 4 completely from scratch. This whole setup, this critic and artist duo, is the heart of what we call a variational autoencoder. And the way they get better is this really beautiful feedback loop. A real image goes in. The critic, the encoder, figures out its recipe. The artist, the decoder, tries to redraw it using only that recipe. Then the system looks at the new drawing and compares it to the original. If the drawing is just a blurry mess, well, both the critic and the artist get a little nudge to do better next time. They're constantly learning and improving together. Now, this whole process is a delicate balancing act. The model is basically being told to do two things at the same time. Job number 1 is pretty obvious. Make the new drawing look as much like the original as possible. Simple enough. But there's a second job, a regularizer, which is just as important. It basically tells the system, hey, keep your recipes neat and tidy. It punishes the model if its recipes get too messy or complicated. And this balance is everything. It forces the system to find recipes that are not just accurate, but also simple and organized. Okay, but there was still one more massive hurdle to clear. To get that nice, smooth map of ideas we're aiming for, the critic can't just give out one single perfect recipe. Instead, it gives a range of possible recipes, adding a little bit of randomness into the mix. Now that's fantastic for creativity, right? But for training a neural network, it's a complete nightmare. It totally breaks the math they need to actually learn. I mean, think about it. If your model makes a random guess and the result is terrible, what do you fix? How do you know if the model made a bad decision or if it just got unlucky with the random number it pulled? You can't tell. And that's a huge, huge problem when you're trying to teach something to get better over time.
The solution to this is an absolute stroke of genius. It's called the reparameterization trick. So imagine you're teaching an AI to throw darts. Instead of just saying, hey, throw a random dart somewhere near the bullseye, which is impossible to learn from, you change the instructions. You say, okay, I want you to aim for this exact spot, and I'm going to add a little random wobble to your throw. See the difference? The AI is no longer in charge of the randomness. The wobble is external. All the AI has to learn is where to aim and how tight its grouping should be. This incredibly clever trick is what finally unlocked the whole training process.
So, after all of that math, all of that training, what do we actually get? What has this model learned? Well, the result is something seriously cool. It's basically a map of ideas. Let's circle all the way back to this image from the very beginning. This isn't just a jumble of fake numbers. It's a picture of that latent space we talked about, that world of all the possible recipes. What the model has done is learn to organize everything, so all the recipes for the number 6 are clustered together in one neighborhood, all the ones are in another neighborhood, and so on. And here is where you really see the magic. Because this map is continuous, you can actually travel through it. You can pick a spot on the map right between the 9 neighborhood and the 3 neighborhood, hand that recipe to our artist, the decoder, and it will generate a totally new number that looks like a perfect blend of a 9 and a 3. It didn't just memorize examples, it learned the concept of what makes a number a number. So the authors gave this whole system a formal name, the Auto-Encoding Variational Bayes algorithm, or for short, AEVB. It's the whole package, the critic and artist setup, plus that clever reparameterization trick, all rolled into one powerful framework. So the big question, did it actually work? Oh yeah. The paper shows that when they put their AEVB algorithm up against the best method at the time, something called the wake-sleep algorithm, it wasn't even close. AEVB was way faster, and it found a much better solution in every single experiment they ran. This wasn't just a tiny step up, it was a massive leap forward for the field. So yeah, AEVB was a huge success. But its real power, the true breakthrough, wasn't just about making sharper-looking numbers a little bit faster. It was about creating a general-purpose tool, a recipe, for learning the hidden structure of any kind of complex data you could throw at it. I mean, take a look at this. The authors took the exact same method and just pointed it at a data set of human faces. And what happened? It worked. It learned to generate totally new, believable-looking faces by wandering around its own internal map of face ideas. And what's really amazing is that in the paper itself, the authors basically laid out the roadmap for the future. They suggested it could be used for deeper models, for video, for all sorts of other tasks. And you know what? In the years since this paper came out, researchers have done all of that and more, building a huge part of the field of generative AI right on top of these ideas. And that brings us right back to where we started. If a machine can learn not just pixels, but a structured map of ideas, and then wander through the empty spaces between those ideas to create something that's never existed before, is that a form of creativity? This paper didn't just give us a powerful new algorithm. It gave us a whole new way to think about what imagination itself might actually be.